In this video, our goal is to learn how to test hypotheses regarding the difference of two independent samples. Note that this test is different from the previous one where we had two dependent sample units. So in this case, we're dealing with the difference between two independent, keyword independent means. In order to carry on this test, a couple of important initial steps must have been met, or conditions or model requirements. One, the samples must be obtained using simple random sampling or through a completely randomized experiment with two levels of treatment. Two, the samples must be independent, of course, since we are conducting a test of hypothesis regarding the difference of two independent means. Then the populations from which the samples are drawn must be normally distributed, or the sample sizes themselves must be large enough. And then lastly, for each sample, the sample size must not be more than 5% of the population size. So to take an example, a simple example to begin with, we have population 1, population 2. We would like to compare the grand or population averages of these two populations. And we have collected sample information here. You have the sample size, the sample mean, the sample standard deviation for each of the populations, or for each of the samples rather. And we have to assume that both populations are normally distributed, which means they meet that condition there. Question A, we would like to test whether the first mean is significantly different from the second mean. So remember, what we are required to test always goes to the level of the alternative hypothesis, whereas the null will be mu1 equals mu2 at alpha equals 0.05 level of significance. So with that said, using the given information, we can use StatCrunch to help us get the p-value we need for this test. So in this case, we're going to try to find the p-value using StatCrunch. In StatCrunch, what you need to do is this. Let's go to StatCrunch. I will go to Statistics. You go to T-stats. Earlier, when we were working on dependent samples, we used one sample. When we're dealing with independent samples, we use two samples with summary in this case. So he's going to ask you for the sample mean for the first sample 1. So going back here, this is my sample 1 statistics. So what is the sample mean? That is 11.3. So that's my X bar, 11.3. And then my sample standard deviation is 2.6. And the sample size for the first population, drawn from the first population, is 11. So I have, let me put that here, 11. And then I'm going to do the same for the second sample, and I'll be back. Here on my screen for the second sample, I have the sample mean, which is 7.8, which is your X bar. So X bar for the second sample, 2.3 is the sample standard deviation for the second population, and 11 is the sample size there. So with that said, the alternative hypothesis is mu1 not equal to mu2. So I'm going to set that up, ensure that this is not equal to, and then I would like to show my critical value. In this case, what is my level of significance? 0.05. So let's see if I have that already. I do. So compute. And with that said, you have your p-value, which is 0.0033. So the p-value here is 0.0033. And the decision rule, as usual, DR, is if the p-value is less than alpha, reject what? The null hypothesis. So I need to check if that condition is met. My p-value is 0.0033, and the alpha is 0.05. So my conclusion is ready. P-value is less than alpha, So we reject the null hypothesis. So our rejection of the null hypothesis means this is the bad one, and in this case, this is good. Remember, that's what we wanted to test. Oh, we are taking it definitely because there must have been sufficient evidence in the sample data gathered to conclude that the two populations have different means, not equal to. Then the second part tells us to construct a 95% confidence interval for their differences. To do that, go back. You can edit the options here. Go to edit. This will take you back to where you started. And rather than perform a hypothesis test, we will construct a confidence interval. At what level of significance? Let's see. Or what confidence level? If our alpha is 0.05, then our confidence level is 0.95 or 95%, which we already have by default here. All right, so compute, and I have the lower limit, 1.314, and the upper limit, which is 5.685. I have brought the results of the 95% confidence interval. I've brought it right here. So as it stands, I have all of what I want from the output here. And of course, we can say that we're 95% confident that the difference between the two averages lies between these two values. We now proceed to another applied example. A researcher with the Department of Education followed a cohort of students who graduated from high school in a certain year, monitoring the progress the students made towards completing a bachelor's degree. One aspect of his research was to determine whether students who first attended community college took longer to attain a bachelor's degree than those who immediately attended and remained at the four-year institution. The data in the table below, or to here, summarize the results of the study. Complete parts A through E below. Question A. What is the response variable in this study? What is the explanatory variable? In order to answer this question, we can go back to the question and note something, and that is this line. One aspect of his research was to determine whether students who first attended community college took longer to attain a bachelor's degree than those who immediately attended and remained at a four-year institution. In other words, this researcher is interested in if the use of a community college or not impacts the time to graduation of the students. So the explanatory variable is the use of community college or not. We want to see if a student's use of a community college or not has any information to explain how long it takes to graduate. Question B, we are to explain why this study can be analyzed using inference of two sample means. The reason why the study can be analyzed using inference on two sample means is as follows. One, the samples are independent. Those who used the community college have no connection immediately with those who do not use community college. Then the sample sizes are large. You can see 267 and 1197. And then the samples can be assumed to be random. And fourth, the sample sizes are not more than 5% of the entire population in the United States, or even all over the world. Then question C, does the evidence suggest that community college transfer students take longer to attain a bachelor's degree? Use an alpha of 0.05 level of significance, perform a hypothesis test, and determine the null and alternative hypothesis. So how do we do this? The first step is I am going to partition my space here. I would like to set up my null and alternative hypothesis, and I'm comparing the means of two populations. I am interested in those who attended community college. I'm not going to write the same, I'm just going to shorthand it here. Community college, and those who had no transfer from community college. So those who attended community college, their mean time to graduation versus those who had no community college and did not have to transfer. Our goal is to test if those from community college, if the average time it took community college transfer students, if they take longer. So if the average from community college is greater in time than those from from community college. So this will be greater here, and this will be equal to here. And alpha is 0.05 level of significance based on the results. So the next step will be to determine our test statistic and also to get the p-value of the test. So let's do that. And we're also going to get the p-value, the critical value. In fact, what I would suggest, just so that it aligns with what you have earlier, is let's get the test statistic, and we're going to compare it versus the critical value using the classic approach to begin with. So how do we get the test statistic? Let's go back to the data set we're given, or to the sample information we're given. So this we're going to take to StatCrunch. So let's go to StatCrunch. Here I am in StatCrunch. I will go to Statistics, T-Stats, please to sample with summary, because we already have a summary table here. So with summary, and for the first population, sample 1, the average time it took them was 5.41. Where did I get this average from? Let's go back. Sample mean, 5.1 for the first population. And then I will go to the next one. What is the sample standard deviation? So for that same group, the sample standard deviation is 1.172, and the sample size is 265. So let's do that. So right here on the screen, I have what? The sample 1 statistics coming from our notes. All of these details. This is the sample size, the sample mean, the sample standard deviation. And for students who are not transferring, because they've always been in the 4-year institution, here are their values. So I also keyed that in for the second sample. Then I need to indicate that I want to perform a hypothesis test, and the direction of my alternative hypothesis, let us check that. It should be greater than. So I need to alter that. So I'm going to go back and alter that to greater than. And then for the next part, my level of significance is 0.05. Let me indicate that in my critical value. All right, that comes preset by default. So compute. Now that I've computed that, I have my test statistic, which is 12.08. So test statistic, and I have my critical value here. So our test statistic is 12 points, as we saw earlier, 12.08. And for the critical value, I can draw the distribution here. And this is a single one-tail test. So for the one-tail test, here we go. And the value here, what is that value? That's the critical value of 1.649. So let me take that back, 1.649. So immediately I can see that my test statistic will lie in the rejection region. So I can see that the rejection region is any value greater than 1.649. So as it stands, that means I am going to reject the null hypothesis. So as we said earlier, since the test statistic of 12.08 is greater than 1.649, it's on the number line, it will fall in the rejection region. Thus, we reject the null hypothesis and conclude that the evidence suggests that we have enough evidence for the alternative, which indicates that community college students take longer than transfer students to attain a bachelor's degree. Then let's see the same question continues in the same context. Question D, we're to construct a 90% confidence interval for this difference to approximate the mean additional time it takes to complete a bachelor's degree if you begin in a community college. So let us see what that is. We go back. Since we still have the same result, you can go to options, edit. I still have all the details there. This time, rather than performing a hypothesis test, I will indicate that I would like to construct a confidence interval, which is 90% in width. So then I would like to show the critical value. So compute, and in this case, you have 0.812 to 1.068. Okay, so let's take that to our working space. Right here on the screen, I have the 90% confidence interval, which goes from 0.812 to 1.068. Well, what you immediately observe is that 0 is not here. So since 0 is not in that interval, it means the difference is not nothing, is not 0. That is, the difference is more than 0. It is significant, it is considerable. So it means that it definitely takes what? Longer for students who begin in community colleges to complete a bachelor's degree as far as this data set is concerned. And that is what question E is asking. Do the results of part C and D imply that community college causes you to take extra time to earn a bachelor's degree? In this case, what we are learning is association, not causation. So the correct answer here is no. What we have observed is that there's an association between starting in a college, in a community college, and taking longer. We did not say that it will always cause it. So please note, in this case, association or correlation does not imply causation. And another reason is that this is an observational study. So because it's an observational study, we cannot claim causation because it is an observational study. We cannot claim causation. So because, again, it's an observational study, we cannot claim causation in our analysis.